Lab 5, Convolutional Neural Network. In this lab, we will be applying a multi-layer convolutional neural network to digit recognition task, and we'll be calculating the accuracy of recognition as well. Convolutional neural network. Convolutional neural networks are biologically inspired variants of multi-layer perceptrons. It is mostly used in some of the very interesting computer vision applications such as Facebook photo tagging, self-driving cars, image classification applications, and also for natural language processing applications. In simple terms, convolution is a filter or a kernel applied to an image matrix where the kernel depends on the type of effect that you want on your input image. In convolutional neural network, we deal with several layers of convolutions and we apply nonlinear activation functions to the results obtained. In here, we deal with a region of an input image. That is, we don't really bother about a single input intensity value. Instead, it is a region from the input which is connected to the neurons in the output layer. Okay, so that way there is better performance and there is lesser requirement on the memory. Okay, now during training phase, depending on the type of task that you want to perform on your input image database, convolutional neural network learns the values for filters or for the kernels. Pooling is an operation which is applied after convolution. What it basically does is it gives you a summarization of outputs from our neighboring neurons. The general types of pooling involved are max pooling, average pooling, and L2 norm pooling, among which max pooling is found to be giving better results than the other types of pooling. Max pooling does a max operation on the convolution results, and by doing so it extracts the most salient feature information from the convolution results. So this way it helps to reduce the amount of computation in the network and also helps control overfitting. Now to determine the shift factor for our filters and kernels, we use a factor called as the stride size. That is, we use the stride size to decide how much we want the filter to move in each step. The larger the stride size, lesser is the number of filter applications on the input data, and that in turn means our output size is also going to be smaller. The arguments that are required for the convolution function in TensorFlow are input, the filter, strides, and padding. So the algorithms that are used for padding are same padding algorithm or the valid padding algorithm. The same padding algorithm is like the zero padding that we have in image processing, and the valid padding is like no padding. Okay, so now let's move over to the programming part where we are applying convolutional neural network to digit recognition task. So here is the program to do digit recognition using convolutional neural network. So First of all, we have a couple of functions in here. So this would generate me the weight tensors. They are random values using truncated normal distribution. The bias variable is a constant tensor. Convolution layer is done using con2d function. So that takes the arguments x, which is the input, and w is the filter. Strides is that which indicates the shift factor for our filter. It takes two types of formats, and these formats they vary with respect to how the data is stored in here. Okay, so this one by default it takes the NHWC format, which means the stride takes the data in the order of batch. This indicates a batch, and this one is the height, this is the width, and this is the channel. Okay, the next argument is padding. So it takes there are two types of padding algorithm that it accepts. One is sane and the other one is valid. In the next function, this is a pooling operation. So the pooling operation that we are dealing with over here is average pooling. What an average pooling does is it gives an average on the input values that the filter is considering at a time, and that's decided by k size. So k size over here indicates the size of the filter for the input tensor dimension. So here's the first layer of convolution. Here we have weights and the bias values getting initialized here. The weight tensor has a shape 5, 5, 1, 32, where 5, 5 is the patch size, 1 is the number of input channel, and 32 indicates the number of features that will be computed at the end of layer 1. Okay, so the convolution function takes input as a four-dimensional tensor. So now our next job is to generate or to reshape our input image to a four-dimensional tensor. So for that we use tf.reshape command, where it takes the input x, that is our input image, and this is the shape to which it has to be reshaped to. 28, 28 indicates the image dimension, and 1 is the input channel. So now the reshaped image is given as input here in my convolution, and that is convolved with the weight values. The output is added to the bias values. So the result obtained is fed as input to the activation function ReLU network. So now this is subjected to the pooling operation over here as this. So it goes through an average pooling and it gives me the output h underscore pool 1. So here as you can see we are in layer 2 now. So the output from layer 1, that is h underscore pool 1 after pooling operation, is used in layer 2 over here to get h underscore conv 2, and this is then subjected to the average pooling again to get h underscore pool 2. So as you can see, the number of features are increasing. As it increases the weight variable, the shape in each layer is also changing. So we repeat the same steps for 3 layers over here. So these are my 3 layers, which involves convolution and a pooling operation, which also includes an activation function ReLU. Now at the end of 3 layers, the image size is reduced, and now we add a fully connected layer which has got 1024 neurons, which will process on the entire image. Okay, so we reshape the tensor into a group of vectors here using the tf.reshape function, and that is used to multiply with the weight matrix and added with the bias. So the result here, even in the fully connected layer, is fed as input to the activation function ReLU. Now to reduce overfitting, we use a dropout layer. So that takes the arguments x and a probability value. So x is nothing but the output from the previous layer, that is h underscore fc1. It carries out this operation and it drops out those values that are not really acting on. Now w underscore fc2 is the new set of weights, and it has generated the corresponding bias values as well, which will be used in the last layer, that is a softmax layer. So here we are using the result obtained from the dropout layer with the new weights. It carries out a multiplication operation. The bias value is added here and is fed to the softmax layer. The training phase over here is just similar to what we had dealt with in the previous lab, except for the training function used here. This uses the Adam optimizer algorithm here. The result obtained is then subjected to a correct underscore prediction operation, which will check if the predicted result and the target result are one and the same or not. In the next step, the accuracy is calculated to see how accurate the results are. So here in the loop we are running it for 20,000 loops. At each loop we are getting a batch of 50 images, and at every 100 iteration we will get to see the training accuracy. Okay, and at the end of all the 20,000 iterations we will get to see the test accuracy. Okay, so now let's run this program and see how accurate our convolutional neural network is on the MNIST dataset. Okay, at the end of 20,000 iterations, it gave me a accuracy of 99.3.